All right. Let's get the last few stragglers inside, and we'll get started. If you're thinking that, oh no, there's a bearded guy in a flannel shirt going to talk to me about programming, and you're scared of huge words and difficult theory, you might be right. So this is in praise of programming minimalism. My name is Stian. I work as a newsroom developer at NRK. That means I help out making news more understandable, comprehensible, and exciting. And also in my spare time, I like to tinker with weird programming languages and creative programming, which I guess makes me like the overlap in Dylan's Venn diagram from yesterday. This talk is about programming minimalism because sometimes programming to us programmers is as water to the goldfish. It's easy to take things for granted or get stuck thinking we have solved the problem. A little careful consideration and exploration is both fun and necessary every now and then. As well as reminding ourselves that what water is smart. Minimalism at its core isn't really about owning the fewest things, even if you could make do with fewer things. And therefore, I'm not going to like Marie Kondo your favorite programming language or try to convince you that there is some sort of programming language out there that is more virtuous to use for some measure of virtue. That's not the point. Code is immaterial, it will be pointless. And if you get that pun, come talk to me later. Just like we would examine our lives and ask ourselves every now and then which things we value and what things have a positive impact on our life, we could examine our programming languages and ask ourselves which parts we value, and which parts have a positive impact on our programs. Like, dear undefined, what's your value? That would be an interesting conversation to have. And to truly answer that question, we would have to take away all things. Remember to laugh, man. Okay, more ha or something. But no, really, taking away things teach us about their value. And even if the point isn't whether we can do without it, taking the time to consider each piece of a big puzzle is an interesting mental exercise in and of itself. Also, like satisfying your own curiosity is a perfectly valid reason to do something. And you might end up making a tiger or something, which is a pretty cool thing to do. If we're going to talk about taking apart a programming language, we're going to have some idea of what a programming language is made up of. And here comes syntax and semantics, two of the most exciting words I know. Syntax dictates the form of a program, like the shape of things, which rules they have to follow in order to make a valid program, and so forth. And then you have semantics, which dictate the meaning of a program. So given like a syntactically valid program, the semantics dictate what the program does. Given these two programs from two different languages, I picked one language that's hopefully familiar to you guys, and one language that I find interesting, and I'll leave it to you to figure out which one's which. Here we have two languages, two programs. They are syntactically similar, but they evaluate as two different things, so they are different in semantics. If we change a little bit around, we get something that's semantically similar, but have a different syntax. So syntax and semantics are deeply interconnected. If you want a thing to have different behavior in a different context, you usually reach for syntax to make that happen. And especially in programming languages, where relying purely on contextual information is highly impractical. Like when you're trying to parse natural language, you can always look around on the words surrounding the word you're trying to find the meaning of. But that is a computationally difficult task to do, so you try to avoid doing that in programming languages. And as an aside, looking into semiotics, here we have a class dog that extends animal. It can speak, and it is a good boy. Its name is Jölle. And even though Jölle is a dog in this program, Jölle isn't actually a dog. This is not a pipe and all that stuff. Jölle is an abstract representation of a dog. It's like a symbol, if you will. And we only interpret Jölle as a dog because we have an idea what a dog is. It's an animal that barks and is a good boy. And this interpretation process, that's semiotics and that's not semantics. Just to make that distinction. And also, semiotics is a whole other talk. If you're interested, there's a talk called Metaphors You Compute By. You should check it out. OK, so applied minimalism. How do we go about this? So this is what we're going to do. We are going to take a piece of code, take away the things, and examine what happens. Easy. When we hit something nonsensical, we go back, because nonsense is inherently uninteresting, sometimes at least. If you have a program that, for some kind of program that evaluates to like the number 1, you could replace the entire program with just number 1, but that would be just nonsense. It's not interesting. And when we hit something interesting, we will stop. So we'll begin here with this totally not contrived example. We have like a tiny add function. We have some variables with names. We have this partial applied function. I hope you can read this stuff. And we have some method program calculation that does something. And the first question we could ask ourselves, what if we could do like without operators at all? Operators are finicky, they are different, they cause us to use like infix instead of application, which is something that's different. So what if we, instead of having the minus in our code, we take it out, put it in stick in a function, and we replace the error variable we had earlier with just a partially applied function that gives us, like, encodes the meaning of what it means to be without error. It's the subtract function with given a 1. And then we can replace the minus operator in our program, and we get rid of some parentheses and all that good stuff. We can do that with all the operators. We don't actually need to keep them around in our program. We do the same thing with equality and modulo. And we can like encode the meaning into whatever fine step is. And we can say that something is acceptable if it's equal to 0. We can replace all the operators in our tiny little program. And now we just have a method function instead. That's nice. So what if we could just compose all those functions? This has been JavaScript up until now. Now it's starting to veer into like fantasy territory instead. We can just stick those functions in a pipeline and apply it to the value, and that gives us the same result. Or we can just imagine some new syntax that's like composing syntax. That would be nice to have. And now we're completely into fantasy territory. The functions are still the same. And you can notice here that all the functions have like basically the same signature. It takes one thing and applies it to a function. So we can compose this cleanly without any extra fiddling. So what if we didn't have all these multiple arguments and we can fix the signatures of our base functions instead of just the compose functions? So let's imagine that we don't accept taking arguments into our functions. We just have this like generic arguments thing that we can read values off of. And then we just have to rewrite it like this. And our program still works the same, so that's good. But what if that arguments function instead was like this global place you can just put values, and all your functions just read values from that global thing? So instead of having a value that is 0, you can have a value function that just puts 0 into your global state. And that would be nice, maybe. Like now our program probably doesn't run anymore. It just returns whatever, I don't know. It probably crashes because you don't really put anything back onto the stack. So yeah. And what if, like, to solve this problem of our code not really executing properly, we could just like make the function not really return things. It just would just push the result back onto whatever the global thing is. and you just have this add function, and you, instead of like accessing the top and the second top of this global thing, you can just pop off it, and you can do the calculation, and then you can push the result back onto whatever this state thing is. And you can just, because you no longer require the plus sign to be in your code, you can just call the function plus instead, and then you have like rewritten plus to be something else. So now we have a program that looks like this. Because it's our own program and it's our own fantasy world, we can just stuff all the functions into the standard library and don't have to worry about them anymore. And we can rewrite our earlier functions and make them into compositions of like this weird push function, and whatever operator function we have already made. So yeah, and because ordering matters for some functions, like if you remember that the modulo function requires us to have the A first and then the 4. Maybe writing the code like this wouldn't work, so you have to do some fiddling things. And we introduce some kind of swap function that will make sure that the top 2 elements on this global state thing is swapped around, so that your function gets things in the right order again. You can do the same with the error function. And now your program evaluates again. It's nice. And instead of calling it args, we can just call it state, and we just have one global state for the whole program. That sounds like some people just call that nonsense, but bear with me. So what if we made, instead of having functions that produce values, we just made values functions instead? Like, because everything in our program is now a function, we don't really need to distinguish between functions and values. So you can just have, like, a value is just a function that produces the value of its name. So now the value 0 is not a value, it's a function that puts 0 onto the state. And we can do that with all the functions. And then we still have our nice program. So now our program is made up of only functions, and also like function aliases, I guess, and composition. And we're still using this composition operator or syntax or whatever, but because everything is now a function, we don't really need to be explicit about this syntax anymore. We just remove it. And suddenly our program looks very different. And also because we have reduced what a function can do in a context, we also don't need the function application syntax anymore either. They can just be implicit. So now we have basically a syntax-free language. It's nice. And what if we got rid of everything but the functions, and we were left with just this weird string, which actually just still computes the same value. But some things are just too good to give up, like giving away ability to name things and give meaning to your program. That's veering into nonsense territory, and we don't want to go there. So we're just going to keep the naming conventions, and maybe like swap syntax around a little bit. We don't have to use like equals for assignments, because why? We can just use equals for actual comparison instead. So our math friends are happy again. So this is where we started, a totally normal JavaScript program. And this is where we ended up, in some kind of fantasy weird language where everything lives on a global state and everything's a function and you have no values. So this is like the easy introduction to concatenative programming. I apologize for the very strange and weird journey, but it was done to hopefully give you a hint on as to what makes concatenative programming tick. Because concatenative programming, in concatenative programming, you make programs by composing functions. That's all you do. As opposed to most other programming languages, which work by applying functions to values. So you have like this split between concatenative and applicative programming. There are no values, at least not in the traditional sense, as I said a few times. What looks like values actually aren't values. They're functions that produce that value so that you can compose things nicely again. Who knew that the empty string could be a function? Every function has the same type. It's a function from state to new state. Actually, like you don't really have to put the state in there. You can just have a function that takes nothing and produces nothing. Everything is just behind the scenes. But for the sake of clarity, we can say that every function takes the global state and returns a new global state. And the state in this case is usually a stack, because stacks are simple. It could be anything, but having something that has very simple semantics makes it so that the way you implement this kind of language is actually doable and not just painful. Because of the fact that the global state usually lives on a stack, concatenative programming is often referred to as stack-based programming. I don't really like this term because it veers into like this Turing tar-pit area of programs, like brainfuck and all those other programs that are just operating on a stack. Concatenative programming is about so much more, and the stack is kind of the least interesting part anyways. These languages are not a modern phenomenon. They have been around for a while. Probably the two most well-known examples are Forth and Joy. And Forth is like really, really old for a programming language. And these two languages also happen to represent two very different approaches to concatenative programming. Forth was created by Charles H. Moore in the 60s, and it was made to program directly on CPUs as an alternative to assembly. And it was designed by Chuck Moore to be simple, portable, and human-friendly. Portable because he was so sick and tired of all these processors having different specs for their registers, and like the only thing that all these processors had in common was a stack, so he just based his language on a stack. And he wanted it to be human-friendly, so he wanted it to be like word-centric, so it looks like written language. And it had to be simple, so he could implement it and take it around with him. Actually, there's a picture somewhere on the internet of a case with these punch cards that are like the first to fourth compiler. Yeah, and Forth has seen wide and varied use since its inception in the 60s. It's out in space on some kind of space probe, and it's been used in like embedded systems still is to some degree. And then you have Joy, which was created by Manfred von Thun, because he wanted a simpler lambda calculus without variable bindings. And that's the sort of idea you only get when you're living in Australia, where like the fauna tries to kill you on a daily basis, trying to simplify lambda calculus. He was inspired by Bacchus. He had made like a theoretical language called FP, and also the SKI calculus from combinatorial logic. And that made up Joy. So Joy and Forth both ended up in this same place, with mostly the same semantics, mostly the same syntax, but they were following like vastly different paths to get there. Forth was practical, Joy was theoretical, but still they ended up in the same place. And that says something about the power of simple semantics driving a simple syntax, which I find kind of interesting. So we have this programming language that's supposedly really excellent at composing programs. So the natural thing to do would seem to implement some of the stuff from Peter Henderson's seminal 1982 paper, Functional Geometry. Or actually, we're going to use the 2002 revised version because that's just easier. So the basis of this paper is to construct a tessellation. A tessellation is math speak for covering a plane with repeating images that completely cover the entire plane. Or this. This is a picture from that paper. It's an approximation of MC Escher's square limit. And we're going to try and make that using HTML Canvas API and also a concatenative language implemented in JavaScript. And yes, I committed the sin of implementing my own language, so more on that later. The paper outlines 3 basic operations: flip, turn, and toss. Or actually, the paper calls it something else, but these are better names. In addition to those 3 operations, the paper also defines the operation over, which groups images that belong in the same box. We don't really need that operation because the canvas just does that by default. All right, so flip. This is the implementation of the operation flip. Flipping around the central axis, like the y-axis of this figure, can be done by scaling with a negative value along the axis you want to flip. Like, so if you scale by -1 along the x-axis, you flip it around the y-axis. And you have to do this negative translation to make sure it ends up in the same place. So if you flip the f around, we get this. If we didn't have this translation, we would end up here, because what we're actually doing is flipping around what the y-axis of the entire coordinate system is. And that, at the moment, it's placed right here at the end edge of the box. So this is flip. And also we have this little translation thing here. And we can just take that out because we want to call it something. It's easier in that way. You just call it center. And then that just makes sure that everything we draw is in the center. And then we have turn. We can implement turn this way. And we can just, because turn is defined to be a counterclockwise rotation of 90 degrees, which is the same as pi halves. And the way we do rotation in the canvas API, or with the canvas in this case, because normally the canvas 0 point is like the upper left corner of the canvas, and and every rotation is around that central point. So what you want to do is make sure that that point is now in the center of whatever object you're trying to rotate. And then you do the rotation, and then you reverse the translation. And because we know that 4 times 90 is the same as a full turn, we can just make our 4 turn functions already, because we don't need to repeat turn all the time. So now we can do turn 0, doesn't do anything. Turn 1, turn 2, turn 3, back to 0. And that's turn. Then we have toss, which is the most interesting function of them. Tossing something in the context of this paper means that you want to rotate it counterclockwise by 45 degrees, which is the same as a quarter pi, and then scale it by the square root of 2 times the size of the box, which means that the diagonal of the new box is the same as side length of the old box. So if you try to do a toss here, you can see that the f has moved around. We can also look at the box. Box restore. Now you can see that the box has shrunk a bit. And the reason we're doing this save restore shenanigans is because when we're applying transforms on a canvas, they are stacking on top of each other. And if we don't remove the translations where the transforms are no longer interested in, they will just keep on stacking and everything just goes haywire. That's why we're doing it like that. Okay, so now we have these 3 operations. This paper also defines a couple of tessellation tiles called t-tile and u-tile. And t-tile is defined like this. I'm not going to read it up to you. You can just look at it. It contains a lot of things. And also u-tile, it's just bigger, but when we start implementing it, it will make more sense. Okay, so let's look at the tiles. And here we have the t-tile. Oops, daisy, there we go. The t-tile. And I've written out the definition of the t-tile a little cleaner. So you can see that the t-tile consists of the drawing of the figure, and it's over the flip-toss version of the same figure, and also a turn-turn-turn flip-toss figure. And since we have made things easier for ourselves by making a turn 3, we can just write turn 3 instead of turn-turn-turn. And this is like the definition of this tile. And already, like it's so much simpler than to actually write out this, trying to convert this function expression into a composition of functions. And the same goes for the utile. The utile is, when you write it out in this way, you can see the symmetry more clearly, because every piece of that tile is just the same figure turned all 4 directions. And if we now go and look at, you can start by looking at the utile. It looks like this. And the t-tile would look like this. At the moment, it doesn't look like much. It looks kind of weird. But it's leading somewhere. And now we have all the parts we need to make our tessellation. We will divide the plane into a 3x3 grid and just fill each cell with tiles such that it completely covers the whole canvas. And here we have our tiles. And I just made these helper functions to define where, which cell in this grid are you trying to paint into. The northwestern one would be the one that starts with 0, 0. And the southwestern one would be 0 times 2 times the box height, and so forth. And then we can choose what we want to draw in each of these. So like you see in the center, we want a utile. It would look like this. We can just maybe do like this, just to make it clearer what we're doing. And if we wanted to put something that goes into the same, you want to cover the whole space, so we make sure that there are no gaps. So we put a t-tile in the corner here. We can see that the 2 smaller boxes of the t-tile line up with the 2 smaller boxes of the utile. And we can just do this, keep going around this, around all the corners, and do the same thing. Turn 1. Of course, there we go. Live coding is always an interesting thing to do in the talk. Turn 2, t-tile restore, and then we can do the same with the last one. Turn 3, t-tile restore. And writing code in this kind of programming language is just like you just insert new code in between old code, and it just works. It's nice. And then we can just go around and fill in all of the sides. We've filled all the corner tiles now. And we can start sticking utiles in all the sides. Following the same pattern, turn 1, utile, turn 2, utile, and also a turn 3 utile. And if we put it all together, we have a complete tessellation. It doesn't look like much, though. It doesn't look like the picture at all, actually. And if we look at our drawing, and we can, this is our draw function. It draws a triangle and it draws a box. And if we don't want to draw the triangle anymore, you can just comment that out. And now we can see the pattern of our tessellation. And if we put something else in here, like a fish, now we have a complete tessellation of the plane using these fancy fishes. Taking away the boxes, and you can see how it looks. And because we now have something interesting, we can start playing around with it, maybe. We can do some shadow color. Shadows are nice. We need some blur, shadow, blur. It's starting to glow, that's cool. If you also do lighter, that was the scariest part of this whole talk, trying to do the right global composite operation correctly. And now we have glowing neon fishes. We can make them even more neon by doing some trickery with the lines. Let's see. Let me do this. Now we have a really glowing neon fishes. Maybe you just swap this around, cyan, and there we go. Now they're looking really evil and lasery. And yeah, this is concatenative programming. And hopefully someone has been thinking like, what was that weird thing you did with the brackets? If someone didn't think that, you will get the explanation anyway. Those are quotations. They are a sub-program omitted from execution within the full program. We can modify quotations using concatenative operations like cons and append, which gives us this ability to make control flow, higher order functions, and recursive shenanigans, which are really nice to have. Like this is a standard REPL for a stack-based language. If we did stick like these 4 numbers into a quotation like this, we made another quotation which would be the function of adding 1 to something. Then we can use a map operation, and we can map over, and that's how it will do a higher order function in concatenative style. Also, you can do like if tests, like control flow. So here we have 3 quotations. The first one is the test. It will execute and inspect the result and see whether it's true or not. And the second quotation will be whatever is happening if it's true. And the last one is whatever would happen if it was false. So in this case, we would put 1 on the stack if it's true and nothing if it's false. So if we execute that with a if test function, we get the 1 back. That's how we would do like higher functions and control flow. Also, you can do something called anonymous recursion, which is really strange. Usually you do recursion by having a named function and referring to that name within the body of the function. But in this case, you can just make recursion without any reference to the function name. So this factorial thing is using linear recursion. It will calculate the factorial of 7 in this case. And also you can implement quicksort using something called binary recursion. And you can do like quick sort and type of sort it. And this looks quite completely bonkers to me. I still wouldn't be able to explain this to you even if I tried. I have to like sit down with a pen and paper and go over this for at least 30 minutes before I'll be able to explain it. So yeah, that's recursion in concatenative styles. And moving on, in praise of simplicity. That should have been the title of the talk instead of minimalism. But I realized that way too late. What surprises me most about like concatenative programming is how little we actually lose. Like most of you have probably seen these stack languages that belong in the Turing tar bit, which have like 6 operators and can make binary numbers and letters, and you can write hello world in like this much code or whatever. But in like this is still stack based, but you still have access to all like the tools you expect to have in a programming language. And sure, we have to do some deeply dissatisfying stack fiddling, which isn't nice at all. And operand ordering for operators like divided by or mod still makes my brain hurt a little bit when I do this. But the meta programming you can do with this, with quotations and stuff, kind of reminds me of Lisp. You have the same thing there. You can quote the list and say unquote, and then it executes the program. It's the same here. And so if you want to partially apply an argument to a bunch of functions, you can just map over them and const the argument onto whatever quotation you're using. And for explorative programming, like what you would do when you're working creatively, like you see with the neon fishes and stuff, it feels really good. Like the lack of syntax getting in your way is it's really nice. And also reordering functions in a pipeline, just you want to do this before this, and you just swap the lines around. And if you want to make a value, produce it from something else, you can just slot it in just between the other functions. And it feels really good to work with. And the runtime for a programming language like this is so surprisingly easy to make. There's a reason why you can find programming languages like this with similar semantics and the whole concatenative style and stuff in the JVM. Like the JVM bytecode is based on this. And in printers with PostScript, because they're so easy to interpret and compile. And also because implementing a compiler for it is super simple. And given how easy it is to create a runtime for a programming language like this, making domain-specific languages and embedding them in your program as an alternative to a graphic user interface seems like a really good idea. I haven't tried it, but I can imagine that for things like an HTML canvas or a WebAudio API, this would be a good user interface. And I want to leave you with this quote from Alan Perlis that says, "A language that doesn't affect the way you think about programming is not worth knowing." And with that, I am done. Thanks for listening, and stay curious. You can find the slides up on GitHub if you want to try it. Also, the slides are fully interactive, so go nuts.